Okay guys, in this video lesson we are going to begin our next unit on work, power, and energy. And we'll get into some torque and some simple machine stuff too at the end of it. Alright, so let's get going. First thing we want to talk about is work. Okay, so in your world, in everyday life and everyday speech, the idea of work is to put effort in, right? Like, oh, I worked hard on that test, or I went to work that day, or man, this is work, okay, that kind of stuff. Now, that's fine, that's our everyday speech. But in the world of physics, the word work takes on a very specific meaning. It's very much like force, or velocity, or acceleration, or we'll learn energy and power and torque and momentum. So these terms mean something very specific to us in the world of physics. Okay, so in the world of physics, when we say the word work, it has to be a displacement caused by a force. Okay, which means something must move for work to be done. Okay, so imagine you could walk up to a brick wall, sit there and push on it and push on it and push on it. You could be sweating, your muscles could be aching, you could be cramping up, and you're doing zero work if that wall doesn't move in the physics world. Okay, you're definitely exerting energy. You're definitely, providing a force against that wall. But for work to be done on that wall, you have to move it. Okay, so keep that in mind as we kind of move forward. That anytime we're looking at this idea of work, there has to be a movement associated with it. Okay. Now, speaking of that movement, in terms of how that works out, as we provide a force to cause this movement to happen, okay, the forces parallel to displacement do the work. All right. In a previous unit, we talked a little bit about how the forces parallel to something can create that acceleration. Well, the reason why behind that a little bit is that only the parallel forces create the work, which then creates that acceleration to happen as you move something. Okay. So if we have a block like this, and we are pulling on it, okay? This could be like a sled in the snow or a wagon with little kids, something like that. And you are pulling on it at an angle, okay? If that block or that sled or that wagon, whatever it is, slides horizontally, okay? The force that you are pulling doesn't account for all the force that creates the work, okay? So only the horizontal force does the work. Now, obviously, we're going to have some friction force fighting against that. So it's going to be that net force acting on this that causes that work. Okay, everything that you're doing vertically here is unused force. Okay, so it's not creating any movement in a vertical direction. All right, so it has to be the direction of displacement and the parallel force that causes that work to happen. Okay, now if that force is not actually parallel, we need to factor that in. So that's where we get this idea of cosine again. So here's our equation. We say that the work that is done is equal to the force applied, okay, times your displacement cosine of theta, all right? So if you're not pulling horizontally and it's moving horizontally, this cosine theta piece is what accounts for that. So what it does is if you're pulling with, 40 newtons of force, you do the cosine of this angle, it'll then give us that horizontal component. So it'll convert this into this for us by doing cosine theta on here, okay? Now, one other thing to make a note of is that we know what force is already, okay? So we know that force is mass times acceleration. So another way to look at this equation for work is that we can say that work done on an object is the mass of that object accelerated over a certain amount of distance or displacement here. Okay, so it's common that we may not know the actual force. We may know the acceleration. We can measure acceleration pretty easily. We may know the mass of the object, so then we can then figure out the amount of work done on that object. Okay, so keep in mind that this equation is our generic equation, but often we substitute in ma for that f in our problems. Okay, now what happens if work is actually in the direction of that displacement, okay? So what happens when that theta is equal to 0, okay? So in your calculator, just go ahead and punch it in. If you take cosine of 0, okay, so go in your calculator, type in cosine of 0 and hit equal, you're going to find out it equals 1, okay? So what that means is that if you have a 0-degree angle, so your force is in the same direction as your work, 100% of your force goes into providing that work or that displacement. So cosine theta equaling 1 is 100% of your force now goes to getting that work done. All right. In those cases, we can actually simplify the equation. So if we have a scenario where we are pushing or pulling something in the same direction or the parallel direction of the movement, okay? So for example, you could say you push the sled, horizontally and it moved horizontally, then you could get rid of cosine theta and use a simplified version of this equation. Okay? You could also put in the ma in here, so work equals mass times acceleration times displacement on that. Now, work, it comes in two different acceptable ways to give it units, okay? So if we go back to our equation here, we know force is a Newton, right? And we're applying a Newton over a certain displacement. So one of our proper ways to label this or to give it units is a Newton meter of work, okay? So it's a Newton of force over meters of displacement, so a Newton meter, okay? Now, the other thing that we can use, and we'll actually kind of learn more why this works later on in this unit, is if you take a Newton's worth of force and you apply that over a meter's worth of distance, that gives us a joule's worth of energy, okay? So technically, when you are doing work in Newton meters, you are actually expending a certain amount of energy, which is in joules, okay? So either label is perfectly proper for measuring for work. So work could be labeled in joules of work or in Newton meters of work, okay? So joules is not just used for energy, it also can be used for work. Because really, we're going to find out later on, the amount of work you do can be equated back to the amount of energy consumed, okay? Now, that being said, keep in mind that joules is a form of energy. So we see over here that a lot of times when we eat like food, we think about the calories that we put in our bodies. But the reality is those calories is a form of energy, so they also can be labeled in joules. So if you were to go to a different part of the world that had food labels, not United States labels, a lot of times they're measured in kilojoules or joules of energy that you're consuming, because those joules of energy, you're given a certain amount of energy that allows your body to do a certain amount of work. Okay, so it all kind of relates back to itself on those things. Now, work itself is not a vector. Okay, we know that acceleration is a vector, that displacement is a vector, that velocity is a vector. Those give us both direction and magnitude. Work is not a vector. However, because work is a relationship of the force doing the work, the sign of work being a positive amount of work or a negative amount of work on something can give us an implication of what's happening to that object. Okay, so let's see what that means for us. So for example, if you have an object that has a positive work happening to it, which means you're going to have a positive force that's going to match the positive direction. All right, so if you have the force in the same direction of motion, you're going to end up getting a positive amount of work done. Okay. Even if you have negative force in a negative direction, right? Negative times a negative is still positive, okay? So it's possible to have negative forces and negative directions here, but because it's force times direction or force times displacement here, those two things could, negative times negative, be positive. So anytime we have a positive amount of work done, that means we are able to speed that object up, okay? And anytime we have a negative amount of work done, that means we're slowing it down, okay? So very often things like friction, applying your brakes, air resistance, somebody pushing against you, that kind of stuff, those are forces that happen in the opposite direction of your motion, okay? So you're moving to the right and the force is being applied to the left, so you have a negative force acting on you, which will create a negative amount of work. So negative work will slow things down, okay? So kind of keep that in mind as we move forward. Anytime we have negative work, it's in the opposite direction or it's slowing you down. And when you have a positive work, that's going to be speeding you up because it matches your direction. Where here they're opposite of the direction that you're moving. All right? All right. Practice time. So what we're going to do is read through the question, solve it, and then I'll put up the answer for you. So how much work is done on a wagon moving 7.5 meters in a horizontal surface by 27.5 newtons of force applied at a 25.0 degree angle from horizontal? Okay, so we do need to factor in the angle now. Okay, go back to your equation, pause the video, solve it, and unpause it, and then we'll get to the answer. Okay, so let's go to the answer now. So we know our equation is this. We're given that much force was applied. We know the height, or sorry, not the height, the distance it moves, and we know the angle at which it was run. So you multiply those together, and we get 186 newton meters or joules, either one is fine, of work done on this wagon. Okay. When we talk work, we often say it's the work done on an object because something else usually does work on another object. So your body does work on a wagon, or you do work on your car, or the car's engine does work on its body, that kind of stuff. Okay.